All right, welcome everyone to the 75th Trees Around the Globe Student Research Campaign webinar. Today, we're going to be talking the state of trees, November 2024, the NISAR mission's role in wetland mapping, advancing environmental monitoring with Dr. Erika Podest. And Dr. Erika Podest is online with us right now, and we'll begin her presentation in a few moments. But first, let me talk a little bit about some of the things we're going to talk about today. And as you know, I like to always pop up a nice little quote. I found this nice one by Annie Prue. She's a fen bog. She wrote a book called Fen, Bog, and Swamp, A Short History of the Peatland Destruction and Its Role in the Climate Crisis. But her quote is interesting quote, but it talks all about wetlands. Wetlands are actually unsung heroes. They nurture young fish, provide refuge to birds, bats, bugs, and sometimes to big mammals like panthers and bears. Mangroves, for instance, are trees and shrubs that inhabit coastal swamps, and they form peat that is home to clams, snails, crabs, and shrimp, and filter pollution out of the water. Their interlaced roots protect tiny fish from ravenous jaws of larger fish, and even manatees and dolphins take refuge there. This is just showing you, this is Annie Prue. And also, here's a picture of some cypress trees in Okefenokee National Wildlife Refuge in Fargo, Georgia. So she writes about this area. So I just want to kind of bring that up as a little teaser to get you, thinking about in your mindset about what Dr. Erika Podest is going to be talking about today. So once again, I'm going to go through the agenda here. Since we are aligning this Year 7 of the Trees Around the Globe Student Research Campaign to what's happening with the 30 years of GLOBE, understanding the past, present, and future. We really want everyone to keep apprised of all the important IVSS updates that are happening all the time. I'm just going to put a slide or two up just to introduce you to wetlands. Erika will talk more about that and how they're researching that. We'll have an introductory video about the NISAR mission, and then our own Peder Falcon, who is coming to us live from Ljubljana, Slovenia right now. He is at the Globe Europe and Eurasia regional meeting in Slovenia right now, where it's a little chilly. But he'll be talking, introducing Dr. Erika Podest, and then we'll have a featured presentation, which is NISAR's role in wetland mapping, advancing environmental monitoring. And then after that, we'll do some Q&A with Dr. Podest. And then we will pass it over to our own Peder Nelson, who will be looking at land cover and forested wetland data. And then we will have some final thoughts and any discussions, and then we will adjourn. Once again, as I always show, the campaign metrics, I'll direct you to the bottom. Year 7 is going very well. We're less than 2 months into this, and we already are at 4,700 measurements from tree height, land cover, and the green up, green down observation protocols from over 1,500 global sites. And for the life of the campaign so far, since the 15th of September 2018 to today, I actually did the metrics this morning, first thing, and we are over 215,000 observations from tree height, land cover, and greenings from over 66,800 global sites. So that's really cool. We've got a lot of data, really looking at that data over time. And this is just, just over 6 years of data with this campaign so far. And as you know, in the GLOBE database, there's well over, I think, 250 million points of observation, data observation in there. But when you look at the 30 years of GLOBE, that's just a lot longer than this campaign. But we're just focusing on these 3 major areas, actually 4 major protocols: the biometry, tree height, the land cover, and the green up and green down. So once again, thank you to our friends there where Peder is located right now, Peder Falcon, to the Globe Europe and Eurasia region and the European Phenology Campaign for all the amazing green up, green down measurements, because the majority of these that you see here come from their hard work working with their folks throughout Europe and Eurasia. All right, so I just wanted to pop this up here. We have the next event for the IVSS 2025, 30 Years of GLOBE, Understanding the Past, Present, and Future, an important date. We have the 4th of December, which is a webinar about badges. So, and on the bottom here, we'll put that in the chat a little later on after I pass it over to Dr. Podest. We have a whole listing there. I took this directly off the website, so you can follow that at your leisure and make sure if you're interested or your students are interested that you check out these informational webinars for IVSS. So I just and I am no expert on wetlands. I will not profess that I am at all, but I wanted to just showcase a couple cool images that I have some of these in my files, and got some of these online. Basically, what are wetlands? A wetland is a land area that is saturated with water either all year or for part of the year. They cover less than 5% of the Earth's ice-free land surface and have a significant effect in the global cycling of carbon and water. These environments are major contributors of methane and are particularly projected to be profoundly affected by global climate change. Hence, wetlands are a part of land cover, hence why we have it as part of this campaign, why we thought it'd be great to have Dr. Erika Podest come in here and talk about the NISAR mission and her expertise with studying the wetlands as part of that, the mission science. So I just wanted to just showcase that a little bit. Okay, now before we start talking NISAR, next month we are going to be doing something a little different for our Trees Around the Globe Student Research Campaign webinar. We are not having a separate campaign webinar. We are piggybacking off of a really, really cool webinar that's going to be happening called, and it's part of the Connecting with the 30 Years of Globe, A Tale of Two Scientists, Changes in Data and Technology Over Time, with scientists Dr. Russ Congleton and our own Peder Nelson. So what I'm going to be doing later today or first thing tomorrow, I will be sending out an email to our campaign participants and members what to do in order to join this. You do have to register because that's a requirement for the webinar with the 30 Years of Globe. You have to register. So I will send you all that information and what to do. And we will be having our December webinar. Our webinar will be this one that is being put on by GIO's Grace Crane Wright with Peder Nelson and Dr. Russ Congleton. Peder, do you have anything else you'd like to say about this? Because you are one of the featured scientists in this webinar coming up on December 5th.
Yeah, this is a really exciting opportunity, not only to talk with one of the scientists who developed one of our protocols, but has spent his whole career figuring out how we measure trees. That is his expertise. And everything we do is built on his foundational work of connecting our tree measurements to our satellite data. So if you have any questions, even if you can't be there, send them to Brian or myself or Peter Falcon, or send them into help@globe.gov, and we will make sure that those get highlighted. And I want you to be thinking as this webinar comes up, what has changed in 30 years? As I mentioned last week in a webinar, highlighting my view of how technology has changed, I was just starting my college career in 1995 when we started looking at and developing the land cover piece of the GLOBE program. So I just want to really highlight how some things are anticipated, some changes are not. And this idea of not only looking back, but starting to think about your own place in this timeline is what we want to have this conversation about. Trees keep growing, as Dr. Podest will really help us highlight. And so the technology that we use to measure them is also changing. And so what we've been presenting here in some cases has been technology of the past. And what we want to really get you excited about too is what is coming on the horizon, partly because Dr. Congleton has revealed challenges with our current methods. What we brought to you still has uncertainty in our measurements. And this is where the new technology that I'm excited to hear about is coming to us. So again, 30 years is a long time. And so help us celebrate what has been happening within the GLOBE community.
All right, excellent. Thank you, Peder. So we'll look forward to that, and look for an email coming out soon, either later today, most likely later today, or first thing tomorrow, showcasing what you need to do to be part of this webinar and how it's going to be different than what we do every month. All right. Now what I'm going to do is I'm going to pop out of this and I'm going to unshare, and then I'm going to reshare again because I'm going to go into the video for NISAR, which will give us a great introduction to what Dr. Erika Podest will be talking about. So let me go ahead and share my screen again. All right, audio tab share. Here we go. All right. That look good on everyone's end there so far? Can you
So
see
far,
that?
looks good.
All right, cool.
It's just black, but it looks like it's
Yeah,
full
yeah,
screen.
black. Here we go.
Are we used to test that by you?
Yes?
You guys beat?
All right, guys, I need you to be quiet though in the other room.
Okay.
Okay, got it.
All right. Okay, we're doing it.
Pretty much anything that you can observe on the land and coasts, and sometimes even in the ocean, NISAR will have an application. Very exciting mission, generating an enormous amount of data that will keep the science community and the applications community busy for a long time.
NISAR is a partnership mission between NASA and ISRO, the Indian Space Research Organization. It's a collaborative project.
And we'll be collecting data for all around the whole Earth for all of the land masses.
Looking at volcanoes, earthquakes, landslides, other natural hazards that occur in the crust of the Earth.
A movement of sea ice, movement of glaciers, how much forest land is growing or being reduced.
Because it can image at night and through clouds, it can allow us to see through storms.
It's really going to allow us to see things changing in areas where we can't with other satellites.
So NISAR is going to open our eyes to the potential of this technique for seeing the ground in places that otherwise has been obscured.
So every 12 days we will map the land masses, and then we can take those mappings and we can compare them. We can do what we call interferometry,
where we can take an image acquired on one day and combine it with an image acquired 12 days later from that same vantage point, looking at the same point on the ground. And when we do that, we can see the motion of the ground down to a fraction of the radar wavelength, which in this case is on the order of a few millimeters.
NISAR has two radars on it, two synthetic aperture radars. One is an L band and the other is an S band.
So it's kind of the Tesla or the Maserati of radars, whichever you think is cooler, I guess.
This here is the radar payload. That is the spacecraft bus. Large 12-meter reflector, common antenna system for both L band and S band to send out the RF signal and capture the return signal.
Good morning, Dr. Paul.
Antanu, how are you today?
Yeah, I'm fine.
The pandemic is something that we were not counting on when we developed this project.
The NISAR project was actually pretty well versed with this remote operations because of that Indian engagement.
There was a little bit of WebEx fatigue, but I think we're learning how to do it better now.
But yeah, we're all in great spirits, and we will take a little hit to the schedule, but we've been waiting a long time for this mission, and we want to do it right. We want the hardware to work, and we want the science to be done.
One of the best things we can do to increase diversity in the sciences is to make it easier for people to enter the sciences.
The data is going to be freely available to everybody. We aren't going to have to pay for it like we do with some satellites.
So making the data free, having it easy to download to your own machine, all of that stuff is critical if we want to remove those barriers to entry to the field.
I'm looking forward to the sense of discovery that I think we're going to have when NISAR data start coming down.
Earth science is incredibly important to understand what's going on in the name of what our children and grandchildren are going to have to face in the future. And all the information we collect now is only going to help them understand that better and hopefully make their lives better.
Digital electronic subsystem, cognizant.
Right, there goes my son.
You know, the radar will...
I can't recall. There we go.
That's our real life here in 2020.
All right. I hope that gave you a little background to NISAR, and we'll be learning some more in a minute. So let me hit stop.
All right.
Don't want that anymore. Sorry about that. Okay, so let me go back and share this one last time so then I can pass it over to Peter Falcon. I'm just going to go pop back in here.
Maybe we can share the link to the video in the chat, Brian, so people, if they want to see that again.
I will share that.
Yeah, thanks.
All right. Peter, do you see this on your screen?
I do. Yeah.
All right. Take it away and introduce us to Dr. Erika Podest, please.
Excellent. Thank you. Thanks a lot, Brian. Yeah, what's very neat about that mission is it was made in part during the pandemic. So it was a nice kind of view to people's lives working from home and all the little miscues. And I thought that video kind of brought that out perfectly as kids are walking by. Kind of showed you that personal life experience of having to do something like that during a very stressful time in life. So with that, I'm going to introduce Dr. Erika Podest, who is one of our JPL scientists. I'm just going to read through her bio really quickly. Erika is part of the Carbon Cycle and Ecosystems group at NASA's Jet Propulsion Laboratory, and she specializes in wetlands. And she's going to be talking to us about her lead role as a science lead in the Wetlands project with the NISAR mission, as well as other things that she's been working on previous to NISAR. So with that, I'm going to go ahead and turn over to Erika. Erika, by all means, please take it away.
Thank you
for being here.
Thank you, Peter, and thank you, Brian. It's great to be here. I'm super excited to share with all of you the role that NISAR will have on wetlands and better understanding wetland ecosystems. So let me just share my screen. Give me 1 second. Okay, can everyone see my screen?
Yep, looks good.
Great, great. So I'm Erika Podest. I'm a scientist at JPL. My focus is in the study of, amongst other things, wetland ecosystems using radar remote sensing. So you saw that video, and I will explain a little bit about radar and the importance of wetlands. I am part of the NISAR science team, the wetland focus area, and I'm also the NISAR community engagement and training coordinator. So that means my role is in ensuring that people understand the data and are able to use the data. So let's start out with NISAR. You heard a little bit about the mission. It's a mission that is being developed jointly between NASA, JPL, and the Indian Space Research Organization, ISRO. And it will be launched early 2025, hopefully sometime in February. It has 2 radars. One is an L-band radar, the other one is an S-band radar. I'll talk about that so you can have a sense of what radar is and what radar does and what are the benefits of radar. And so satellites have a certain repeat orbits, and so the repeat orbit of NISAR is every 12 days. So every 12 days, we'll be seeing the same points on the planet. So we can then have that monitoring capability. It is a global mission, and all the data is going to be openly, freely available. Okay, so let me step back and explain a little bit about the amazing technology that we're using with NISAR. So here's the electromagnetic spectrum, which is the range of energy across the spectrum, and you've got parts of the spectrum that have very long wavelengths like radio waves, and then parts of the spectrum that have really, really small wavelengths like gamma rays, high energy, right? So when you look at Google, for example, images, those are optical images, and those are in the visible range. So that's why we can see those images and we can interpret them, because they're like photographs. So they're taken in the same range that we can see, and we can then interpret the colors. But the truth is that there are many satellite sensors in space that are making measurements in the electromagnetic spectrum, in different parts of the electromagnetic spectrum that are outside of the visible range. The visible range is just a sliver of the spectrum. There all this energy outside of the visible range that we cannot see, but we can measure. And so there's infrared. So for example, you've all seen a thermal camera, you point at someone and you see their temperature. And then there's microwave, the microwave range. And that is where NISAR is making its observations within the microwave range. And it's especially useful because it can penetrate through clouds, and it has very unique characteristics that are different from optical. I'll go into that. Before I start talking about the specifics of microwave, I just wanted to provide a general background on different types of remote sensing data. So you have what's called active, and you've got passive remote sensing data. So active means, or let's start with passive actually. Passive means that you're just collecting the emissions or the reflections within the Earth atmosphere system of energy, right? So a camera is an active, a passive system. So it's collecting energy that's reflected from an object or from whatever it's pointing at. And then there's active, and active systems provide their own source of illumination, and then they measure the portion of the signal that is returned to the sensor. Radar, specifically NISAR, which is a synthetic aperture radar, is an active system. It sends a signal, measures whatever is returned. LiDARs, you've probably heard of LiDARs, those are active systems too. It's sending a signal in the optical part of the electromagnetic spectrum, and it's measuring with the return, okay? So just a very basic distinction between passive and active remote sensing sensors or systems. Now, the advantages of radar over optical is that it has a nearly all-weather capability. Because we're providing that kind of illumination source, that signal and the characteristics of the signal, it can penetrate through most weather capabilities. So most clouds, whether it's dusty or foggy, there's a day or night capability. So we can see the surface regardless whether it's day or night. And the signal can penetrate through the vegetation canopy and provide information about what is underneath the vegetation. And this is where radar is very useful in detecting inundated vegetation and seeing whether vegetation is inundated or not. With optical, you're just seeing the top of the canopy, and you don't know if that vegetation is inundated, if there's standing water underneath the vegetation. The signal can also penetrate through soils and provide information about the moisture content in soils. And also there's minimal atmospheric effects. I know you've probably all seen, optical images where you might have dust, or maybe it's haze. You can't really see the surface that well. Certainly if there are clouds, you cannot see the surface with optical images. So that is a really great advantage of radar over optical, is that you don't have to do what is called atmospheric corrections with radar data. So ultimately, radar is sensitive to two things. One is the moisture content in the surface, and the other one is to structure. It's different types of information than optical. Optical gives you information about the spectral properties, the chemical composition of what's in the surface. Radar gives you information about moisture and structure. The disadvantages is that radar images are different. So think of it as something analogous to an ultrasound, right? So you need a certain training and knowledge about radar images in order to be able to interpret them. They're not intuitive like optical images. And then there's something called speckle, which is like this graininess. And think of an ultrasound, it's kind of grainy. So you need to be able to apply some filters to reduce that graininess. And then topography has effects on the images that you need to account for. I'm not going to get into that, but just wanted to make you aware of the advantages of radar over optical. And this is just kind of to bring this point home about global cloud coverage and really the amazing advantage that radar has over optical in being able to see areas that are constantly covered by clouds. So this image here is a cloud fraction averaged from 2002 through 2015 using data from the MODIS sensor on board the Aqua satellites. So what the colors indicate, dark blue are areas of no cloud, light blue are areas with clouds, and white are frequently clouded areas. So you can see, there are a lot of white areas, and these are areas where there's frequent cloud coverage. And so that's where radar is especially useful, because with optical, there are some places that you hardly ever get an image, a cloud-free image, because in the tropics, you have such prevalence of cloud cover, or also this whole night, prolonged nights, darkness in winter months. You have long hours of darkness, and you can still see the surface with radar, something that you cannot do with optical. Okay, a little bit about radar. All right, so a radar system, with optical systems, you're looking down. With radar systems, you're looking sideways. And the reason for that is because radar is basically measuring the distance or the time it takes for the signal to leave the sensor and return. So if we're looking straight down, and you had 2 points in the surface, points A and B, on like what you're seeing on the left, that signal would be reflected at the same time from both points and return to the sensor at the same time. So you wouldn't be able to differentiate between those two signals. Now, if you're looking sideways, so you've got this sensor moving in a straight line, and the platform is moving in a straight line, but the sensor is looking sideways, like on the finger on the right, then the time it takes for the signal to return from point A and from point B is different. And therefore, you can then differentiate 2 points on the ground. That's the basis of radar. You're always looking sideways, synthetic aperture radar. So what happens is, the sensor sends a signal. That signal, when it reaches the surface, whatever's there, it reflects back towards the sensor. In this case, we have a house and we have a tree. And so through a complex image processing, these radar images are created. Okay, so the basis of radar is that you need to understand what are the surface conditions that cause different types of reflections, right? So with radar, we call them backscatter mechanisms. So that signal that returns back, it's measured in decibels. So we're measuring, like, based on the strength of the signal that you send, what portion or how strong is it, or what fraction of that signal is received? How strong is that signal received? That's measured in decibels. And so depending on how your surface is, you'll have different scattering returns toward the satellite. And the satellite only measures whatever is returned back to the satellite. It doesn't measure what's reflected in a different direction, okay? So you've got a smooth surface. That means, like, it's a surface of water, for example, and the signal scatters away from the satellite. So those surfaces tend to be very dark. Then you have a rough surface where you have a little bit of roughness, and that signal kind of scatters in different directions, and part of the signal scatters toward the satellite. Then you have something what's called double bounce, where you have a smooth surface like a road or a body of water, and that smooth surface causes the signal to scatter away from the satellite. But then you have something like a building or a tree trunk that redirects all of that energy back toward the satellite. And then you've got something called volumetric, which, like, say in a forest, you have the signal penetrating through the forest canopy and basically reflecting from different parts of the forest. And let me just show how that one works. So here you have the signal can reflect from the trunks. It can penetrate all the way through the forest, depending on how dense the forest is, and reflect from the ground to the canopy, to the branches. I mean, there are many different ways that signal can reflect within that volume. So that's called volume scattering. And let me show you how that looks in a radar image. Okay, so we talked about smooth surface. So this is a radar mosaic of the Amazon, part of the Amazon basin. And the dark area here in the middle, that's the Amazon River. So I've delineated with a yellow circle part of the Amazon, a section of the Amazon River, and it looks really dark because it's a smooth surface. So basically, you know, it's a smooth body of water, and that's reflecting the energy away from the satellite. That's why it looks very dark. Then you have an area that has some level of roughness. In this case, these are deforested areas. And so there's no vegetation, but there's some level of roughness, or maybe there are tilled fields. And so there's energy that's being scattered in different directions, including toward the satellite. So you'll have some level of brightness from that area. It's dark, but not that dark, not as dark as a smooth surface. And then you've got volume scattering. Now this is a forest. Again, you've got interactions within that volume, and a large part of the signal is returned toward the satellite. So these areas appear gray, a little higher tone. And then you've got double bounce. So in this case, inundated vegetation. So the signal penetrates through the canopy. It reflects off of that surface of water because you've got water above the soil, right? So that's a smooth surface. It reflects from that smooth surface away from the satellite. But guess what? You've got these tree trunks. And so that is going to redirect the energy back toward the satellite. And that is one of the unique things about radar, is that we can observe inundated vegetation very clearly. Everything you see in this image that is very bright, or almost everything that you see in this image that is very bright, that's inundated vegetation. This is during the high flood season in the Amazon. So it's really striking. You would not be able to see this with an optical image, again, because the signal is basically just seeing the top of the canopy. Okay, so why are wetlands important? NISAR has a very big focus on wetland ecosystems because it's, as I mentioned, it's ideal. We can penetrate through the vegetation and see whether it's inundated, vegetation is inundated or not. And wetlands are areas that are inundated either or saturated either permanently or intermittently, and that they are adapted to these saturated conditions. So they cover, as Brian mentioned, 5 to 6, 7% of the Earth's surface, but account for a disproportionate share of carbon. So there are very large reservoirs of carbon. In addition to that, wetland systems have other amazing benefits. They are flood mitigators. They are like filters of water, sources of food, of biodiversity, of livelihood for surrounding communities. So they're super important ecosystems, in addition to their role as carbon storers. So one thing about wetland ecosystems is that there are carbon fluxes from these ecosystems, and methane production occurs whenever you have anaerobic soil. So in wetland ecosystems, you might have wet soils, but when it saturates and it's stagnant water, you develop anaerobic conditions. So once things are reach anaerobic conditions, is you've got organic matter decomposition by methanogenic microorganisms, and that generates methane. Okay, And so wetland ecosystems, inland wetland ecosystems generate methane. However, through time, they tend to be much larger carbon reservoirs than emitters of carbon, whether it's in the form of methane or whether it's in the form of CO2. But it's very important to understand what is the inundation length and extent of these ecosystems in order to understand how much methane and CO2 they release. Okay, so there are in general two types of wetlands. There's inland wetland ecosystems and coastal ecosystems. Coastal ecosystems are larger CO2 sinks than inland wetlands. And the reason for this is because they don't produce methane, coastal ecosystems, but they store a lot of carbon in their soils. And this storage of carbon by coastal ecosystems is known as blue carbon sequestration. And that's becoming kind of a big thing in terms of carbon credits. And not only that, so it's become now an incentive to protect coastal ecosystems. Coastal ecosystems account for about 1.47 of global wetlands, but per unit area, they store a very large amount of carbon. Then there's inland wetland ecosystems. They also store a large amount of carbon, but they also release carbon, as mentioned, in the form of either methane or CO2. And it tends to, they tend to be more storage of or reservoirs of carbon. However, the concern is with climate change, changing precipitation, increasing temperature, whether these ecosystems might shift from being net reservoirs to net sinks to sources of carbon. So in recent years, and this is one of the concerns, we've been seeing an increase in methane, atmospheric methane concentrations globally. So we try to monitor this via satellites. These are difficult to monitor at a local, on a local basis because it's a very small fraction. It's measured in parts per billion. But there are satellites now that can measure and monitor methane, atmospheric methane, however, at very large scales. So when we look at the wetlands and methane, right, the wetland ecosystems have a very large uncertainty. We see it here. So these are natural sources of methane, wetland ecosystems, and you can see the large uncertainty in parentheses. And so this is why it's very important to be able to monitor these ecosystems, to be able to better understand when they might be producing methane and how this is changing from season to season, year to year, again, because of increasing temperature, because of changes in precipitation in local hydrology. So I'll skip through this, but basically what this summarizes is how difficult it is to really hone down on the methane fluxes. You need models to do this, and models don't perfectly represent wetland ecosystems. So the more information that we can provide to these models about where these ecosystems are located and whether they're inundated or not and how long they're inundated, this helps the models reduce the uncertainties in terms of their estimates of methane production from inland wetland ecosystems. Okay, so these are some of the challenges so far in characterizing wetland ecosystems. Via optical, they're hindered by clouds, and it's difficult to assess whether there's water under the canopy. On the other hand, with microwave sensors, you don't have the cloud issue, and the sensor can penetrate through the canopy and basically detect beautifully all of these inundated wetland ecosystems. And that's going to be the beauty about NISAR, is that we're going to be able to monitor these ecosystems and their dynamic nature every 12 days, actually every 6 days, because we have ascending and descending passes. So we're going to be able to really understand the dynamic nature of these ecosystems and how, again, they're changing from year to year, seasonally, and from year to year. And also monitor, there is a flood pulse here in the Amazon. It's a flood pulse wetland ecosystem. So we'll be even able to see the flood pulse moving down the Amazon. It's going to be fantastic. So these are some of the things that we'll be able to see. These are examples of studies using other types of data that is going to be similar to what NISAR is going to be collecting. So this is L-band data from a Japanese satellite, and this is in the North Slope of Alaska. Here we're looking at open water, so that's water accumulated in the surface in the North Slope of Alaska, and looking at how the water changes across the months because of evaporation or drainage, right? So at the beginning in the spring melt, there's a lot of water in the surface, and that is reduced as the surface gets drier. And then here's an example, again, using data that is similar to what NISAR will be providing. This is from ALOS Pulsar. This is another Japanese, more recent radar satellite. And this is a temporal sequence in the Amazon. In the top, you see the high flood, a lot of bright areas. All of those are inundated vegetation. And look how dramatic and how drastic the difference is between high flood on the top left and low flood on the bottom left, right? So then we can create these mosaics to understand the extent, the difference between inundation extent between low flood and high flood, and map that. And with time series images, we can even then identify which parts or how long different parts of the Amazon are flooded, 1 to 2 months, 3 to 6 months, over 6 months, etc. So, so again, it's going to be extremely useful, especially from the carbon perspective, in being able to monitor at a global level these ecosystems with NISAR and be able to better than constrain these methane observations and methane models from wetland ecosystems. And I wanted to share with you a video, so I'm gonna stop sharing here. I wanted to share a video of a campaign that I supported in the Amazon, because the satellite missions have what's called Cal-Val efforts, right? So the data is going to be openly, freely available. We want to make sure we deliver good quality data. And in order to do that, we need to be able to calibrate and validate the data. And we do that by putting sensors in the ground, in situ, and we compare what the satellite is telling us to what the sensors are telling us. And if they match, then it gives us certainty that the satellite observations or measurements are accurate. So I'll share with you a video. This was a campaign where we're placing sensors in a wetland ecosystem in the Amazon. Let me see.
When wetlands flood, they produce methane, which is a powerful greenhouse gas. In fact, wetlands are the largest natural source of methane on our planet. Knowing the extent and duration of flooded wetlands allows us to better estimate a wetland's methane production, which helps better understand how climate change is having an impact on wetland ecosystems. I recently returned from a scientific field campaign in the Peruvian Amazon. We went to Pacaya, Samaria to install sensors that measure when wetlands are inundated or flooded. These measurements will be compared to what the NISAR satellite will be measuring from space. If they match, then it gives us confidence that the satellite is making adequate and accurate measurements. If all goes according to plan, NISAR will be able to detect and monitor inundated wetlands from space, providing data similar to our ground measurements all year round. So what is NISAR? NISAR is a collaboration between NASA and the Indian Space Research Organization. The satellite will have 2 radars, allowing us to see the surface of the Earth regardless of clouds or day or night conditions. In this campaign, we focused on NISAR's ability to see through the canopy to detect different types of inundated wetlands. And given the dense tree canopy in the tropics, this area will be a test of NISAR's radar to detect inundation through thick vegetation. Our amazing team worked very hard and accomplished our goals for this field campaign. It was hot, it was hard work, it was difficult to access, but it was very productive. We installed over 75 sensors, which are up and running and ready for when NISAR overflies the area. I think this mission is going to be game-changing in our ability to monitor global wetland ecosystems. And that, my friends, will allow us to better understand our planet.
So that's it. I wanted to close with that. I had one more slide. Just emphasizing the importance of NISAR and wetlands.
Ask someone to draw a picture of a planet.
So with that, I'm open to your questions.
Erika, that was an awesome presentation. I really enjoyed all the little videos that helped us understand radar technology. That was extremely helpful, and all the images that you put together. There are some questions in the chat box. Let me go and open that so I can go ahead and ask you. And I know you're short in time, so we won't take too much time. Let's see. One question we have is there more of a focus on coastal wetlands or inland wetlands, or focus on equal, or is it equal with NISAR research?
I'm sorry, can you say again the question?
Sure. Yeah, I apologize. As I mentioned, I'm in an area where there's not great internet. Where's there more of a focus with NISAR? Is it coastal wetlands or inland wetlands, or is it equal?
Yeah, that's a great question. It's equal because they're both very important. Coastal wetlands tend to be a little more challenging because you have this dynamic nature of the tide coming in and out, and things look different in the image based on whether it's high tide or low tide. So it's a little more challenging to analyze the data in coastal wetlands, but we're focusing on both.
And are there any satellites that you compare your data to, like a GRACE? Do you kind of compare that to NISAR data and see how dynamic the wetlands are?
Yeah, absolutely. So we compare to whatever other sources that are of similar spatial resolution that we can get. So we'll probably compare it to optical data, wherever it's available, wherever there's cloud free, to identify different types of wetland ecosystems or help identify different types of wetland ecosystems. And we might also compare it to other radar data like Sentinel-1 C-band, which has different characteristics, but it will be good to understand what are the what sort of complementary information can be gleaned from the other data sets. GRACE tends to be very coarse resolution. So GRACE is on the order of 300 to 500 kilometers. NISAR is on the order of 10 to 40 meters, right? So we'll probably be doing comparisons with GRACE at very large regional areas.
Thank you. Another question. Do we need more wetlands to help with climate change and to balance ecosystems?
Yeah, absolutely. I mean, these are such important ecosystems that it's important to preserve the ones that we have, to protect them, because they have so many different roles, as mentioned, not only as reservoirs of carbon, but also for biodiversity, for clean water, for coastal protection from sea level rise. So it's more of really protecting them and restoring them.
Thanks. Maybe one more question or two more questions. Your field campaign, that looked really fun. What was something fun that you learned from that? And maybe something that wasn't so fun. I imagine mosquitoes must have loved you there.
It was amazing because as a scientist, it's always a reality check to go out into the field and to go out to a place that was pretty remote. It took 3 days on a boat to get to this site, and to be for a little while just disconnected from everything and just enjoy nature, the sounds of nature. That was really incredible. And also to have an appreciation of how other people live with what we think is so little for, from our Western perspective. However, they have all the happiness in the world, and they have a very, just a very simple but happy life. And that's always very eye-opening.
Yeah, and as you mentioned, you can get a really good appreciation for things. So that's always great to see. Last question for you, because I know you have to go. You mentioned a couple different types of wetlands. How many types of wetlands are there?
Oh, there are many different types of wetlands. There actually coastal wetlands, there are not that many types of, say, mangroves, for example. But I can't name them all, but yeah, inland wetland ecosystems, there are many different types of inland wetland ecosystems.
Oh, okay. Well, thank you very much, Erika. If we have any more questions, I can be happy to email them to you at some point.
Yeah.
But thank you very much for your time. I know you really,
Sure.
lots of stuff you're doing, and just once again, thank you for sharing your time with us today.
It's my pleasure. Thank you, everyone, for your interest, and happy to answer any questions. Just please reach out to Peter or to Brian, or feel free to reach out to me as well.
Excellent. Thank you. And I'll turn it over to Brian.
All right. Yeah, I echo Peter's sentiment. Thank you so much, Erika, for the presentation. We've talked about NISAR before, but we just didn't have that in-depth look like we got today. So thank you so much.
Thank you, Brian.
And now I'm going to pass it over to Peder Nelson, and he's going to be talking about land cover and looking at forested wetland data. So Peder, take it away.
Yeah, well, do, Brian. I really appreciated, that insight into something that can be very scary, and but it is really foundational to what we are trying to do in our Trees Around the Globe student research campaign. So trees are that volume, right? And so a lot of our sensors and a lot of even our definitions are focused on what we see first from that satellite. And Brian, talks about this with the ISAT-2 data as this is the top of canopy. And so that's a lot of what we see within the GLOBE program too, is, you know, the first thing is, are there trees there? Are there trees located in that location? And part of that is exactly for what Dr. Podest was describing. Our optical imagery doesn't allow us to penetrate and see what is happening on the ground. And to me, this is this great transition where our globe observer, our photos, you know, some of these things that we're actually seeing on the ground are the insights that we need to be able to help understand those different signals. In particular, we can be the eyes that helps Dr. Podest know, is that water on the ground? Is it on the surface? Is it making the ground muddy? And how long does that persist? And these are some really great things that just having these ground photos in the right place can really provide some insights. So as much as you know, we want to get that tree height, part of that is actually helping us to understand that radar signal, and especially that complex canopy bouncing that Dr. Podest really highlighted at the very end, and how, you know, trees and water can actually intensify a signal. So, you know, this is something that we want to emphasize is our unique contribution to the type of science that she highlighted for us today. Okay, so with that, you know, this is with trees kind of one of these pieces where wetlands are really a soil condition. You know, what is happening with the water at the base of those trees? And this might express itself with the type of trees that exist there, the height of them, and some of these things that we're seeing in place that maybe we're not thinking about as we measure that height of the tree. Maybe the reason why it's that height is because of the amount of water that is in that soil. And as Dr. Podest highlighted, you know, if there's a lot of water oxygenation going on, right, that can actually help the tree roots get some of those things that help them to photosynthesize. But in contrast, if that water just sits there and it stagnates, as she sort of described there, it can actually impede some of that CO2 and the life-giving force that is there. And so, you know, there's a lot of things that we see on the ground that we're trying to understand from, you know, space. It's great technology, but we still have some great things to play into helping us understand this. So again, I want to highlight that, you know, when we talk about forested wetlands, you can have shrub wetlands, you can have grass wetlands, you can even, have that standing water on the surface. So this can be something that the longevity of it is something that our photos can give us insights into. Again, like Dr. Podest really highlighted, you know, these clouds get in our way. So that up photo that you're taking in place not only is giving us insight into tree cover, but also it's giving us insight into whether we can use optical imagery to see this location, right? And if we can't, well, then we need to turn to a different technology. So I want to really, you know, zoom in on, a couple places that I know to show you what a forested wetland might look like on the ground. And these are going to be different around the world. And so I want to focus in on sort of my area of expertise, which is the inland forested areas. And so one place that we can look at sort of climate change thousands of years after those glaciers have left is in the middle of the United States, here in an area of the northern United States where it borders with Canada. And one thing that I'm going to do just to make our life easier is I'm going to turn off the photos, and so we can zoom in a little bit faster here with this. Okay, so today, I mean, one of the things that I want to really stress about seeing these forested wetlands from above is, in fact, they are these really dark areas on the landscape. And part of that has to do with that water absorbing some of the sunlight, the lichens and grasses and shrubs also absorbing some of that light. And so and then you have the trees. It just turns into a complex area where our sunlight just gets lost, is the way that I like to think about it anyway. But here in an area of northern Minnesota, I want to highlight how you can identify some of these forested wetland areas, or areas that could be forested, or wetlands, or areas that might have trees, but the soil is moist for a long period of time. And maybe a place that you want to bring in your soil protocols, right? And start looking at some of those other measurements that help us to decode, is this a wetland, or is it just wet today in this area? Okay, but what I want to sort of highlight is, a lot of times you'll have open water. You'll have in our natural colors, what we're recording with our phones, and with and what we see from the optical imagery, is these black bodies of water, because they're absorbing all that sunlight except for the blue. But you'll usually see something like that, that ends up showing, surface water, or water that is accumulating on the surface. Now, the question is, does it just stay there, or does it start moving out of the landscape? And so, this is where if you start zooming in, you might actually see linear features that are rivers that are either feeding into that water body or are draining out of that water body. Okay, so those are great areas to look for wet soils, areas that might be inundated from, just having a lot of water in this area. So if you look around these areas, one of the things that you'll start noticing is the top of the tree canopy, right? And you can see that tree canopy, you can identify it versus just grass or green areas, shrubs maybe, because of that shadow that's there. This also is what hides the surface conditions of what's happening. Are these wet trees with wet feet, or are they areas that are dry? And so, so when we see surface water in an area, and adjacent to it, we start to see trees with their shadow, that might be an area that is forested wetland. And that's going to have some just different activity going on than right next to it in an adjacent area where it could be shrubs or grass dominated, right? And you can also think about, one is going to be warmer than the other, at the surface. So measuring the temperature of that water, might be something else that you bring into your investigations. And so I want to highlight that you can usually see this surface water interacting with vegetation, and that's a signature of a wetland community, a wetland area, an area that again is challenging. It's dynamic. You might need to wear rubber boots when you go out there. But it's also one of those things that if you can go out there and just do your remote sensing on the ground, you can help us to understand, is this surface water always there, sometimes there, or never there? So again, that can help us to maybe understand the height of those trees in that location, because you will have maybe some gradations of height as you move away from areas that have that wet, dynamic soil to it. Okay, and so I'm going to just zoom out here, because one of the things that you'll start to see as well is, again, a characteristic is sort of this reddish feature when we zoom in, and where we start to see these splotches of green, and these are forested wetland areas in between shrubs. Okay, so that's sort of like this just really interesting color that you will see, and one of the things that you're looking for are these islands of trees that are out there. Okay, so with certain resolutions, that's not very easy to see of our satellite imagery. But as you zoom out, you start to see a larger area. that your individual measurements might actually sit within. Okay, so again, when we zoom out, it's like, oh wow, I see this orangey green color that tends to indicate that forested wetland area. Now again, I kind of know this because of the other research that we've done in this area. So, but in your local community, you might start seeing similar sort of patterns. Okay, so with this, one of the things that that can help me understand this, not just me waving my hands and guessing, or you guys believing me in this is what a forested wetland actually looks like, is to pull up and actually access our ground photos. So one thing that I know for sure, because I was the one that took these, is if we zoom in, one, we have this cloud issue that Erika highlighted for us with our optical imagery. Okay, but here, if I zoom in, and here I'm going to turn off our cloudiness for today, so that we can see this a little bit more clearly. Here, what I want to focus on is we have high resolution imagery, we have green, we have this black, which might indicate water. And then we see, actually, as we zoom in on maybe this particular location, we see a little spider web of black and green, and this is a bog, a forested wetland, a wetland that has some shrub in it, some other things like that. And as we zoom in, things start to pixelate, as Dr. Podest highlighted. And so we have to start using our eyes to maybe see that there's actually like a little bit of darkness in this area that might indicate a single tree standing in this location. These are things that we need to go investigate, right? So let's pull up this picture that's right in this area that's pointed northwards. And wow, what we actually see is, if we look west and look at this photo that is pointed to the left part of our screen, we see trees off to the distance. And that is actually these trees over here on the left-hand portion. They make this sort of dark color because of the shadow. You can actually see that here. And then we also can start to see the wetland area that is primarily shrubs or grasses, right? So let's blow this up. So you might see a landscape like this and wonder why you have this edge of trees. We go to the satellite imagery and we can actually start to see this surface water that appears. Very, very interesting, right? And we can start looking across at some other directions and other photos. And what we start to see here, again, is surface water here that mixes with our vegetation. That's the wetland that we're used to seeing. So again, you might need to put on your boots and walk out there. But one of the questions that we have is, over on this edge where the trees exist, do we have wet soil there that might indicate a wetland area? Or what's happening with the trees that fall down? How fast are they decomposing? A lot of really interesting questions come up, as well as, again, as I look out here, how deep is this water? Is it just at the surface soil level, or is it like this lower corner? So that's what you can start to do with our ground photos. And again, somebody like Dr. Podest can look at that photo, look at the date. Look at this. This was the 22nd of July this summer. Why do we have surface water at that one moment? Okay. And one thing I want to stress here about this is it's one moment in time. Now, a wetland, to define it, you need to actually have water there for a persistent amount of time. And to that question of that length of time helps to define what type of wetland is it. Is it something that's always water, that has this dynamic nature to it, where maybe rain comes in or other things like that? Or is it something that drains and maybe it's only has this amount of water in it for a certain amount of time? Okay, so time is a really important part of our observations. So again, as Dr. Podest highlighted, if on this day, we actually would not be able to see it with our optical imagery. There's cloud cover, right? It's not blue. So I want to encourage you to go through and investigate some of the locations around you through the satellite imagery like this. Look for photos that might be there, that might be describing the edges of water bodies and trees. Because again, this is that forested wetland area that we're really trying to describe very well. And in this case, you know, if we can see through the clouds, great. But if we can't, then we definitely have problems. So again, you know, zooming in on different locations is your friend, and the way that you actually start to recognize and start to see some patterns that you really do need a ground photo to dive into and start to understand that this actually has trees. And when I stepped into this area, I sunk down to my knees in water. So don't be fooled by what it looks like from a distance, okay? We still need those direct measurements, but you might want to do it safely. And just because there's grass there doesn't mean that it is a hard surface. Okay, so again, I had a lot of fun going out and just exploring the colors that were here. You can see that just in this small area that I went investigating, we had a lot of different colors. We even had an area that had trees harvested out of it. And so, you know, again, I want to highlight that these photos really can be a lot of fun as you go trying to understand, you know, is this a wetland area? Which again is only defined by that persistence of water, which really leads us into our soil protocols, right? So land cover and photos like this are one of the fastest ways that we can provide feedback to our scientists, right? And so I want to stress, because you know, this is a particular definition class that you can find in the maps that we've highlighted in the past. Okay, so before we've highlighted this global land cover data set that's out there that actually has a herbaceous wetland class. Now notice they do not have a forested wetland class. And that's exactly because the reasons why Dr. Podest explained, this is a research challenge. It's hard to see exactly why is that area dark. Is it because of the trees, or is it the trees and the soil? Is it the terrain? And so just recognize that right now you might have a hard time finding a map that tells you exactly where these forested wetland areas are. Okay, so this is science right now that we're looking for, and we need your help. Okay, and I wanted to stress this because this was something that in my part of the world just recently came out in terms of a journal article. And this really stressed that our uncertainty in our climate models is because of the hidden carbon that is at the surface, that these trees that we're asking you to measure are growing on, right? So these wetland soils and what is happening on above ground is important for carbon, but also what is happening below ground is important for our carbon. And so, you know, this is one paper that inspired me to dive back into looking at what is happening, you know, in these areas where these trees are growing. So I want to really, you know, stress that this is current science. We need your help actually improving our maps so that we can improve our estimates. And luckily, there's tools that make this easier. Okay, so I'm going to end here because, as Dr. Podest said, it takes a while to start understanding what a satellite is measuring in locations. Okay, so getting you data is our first thing that is really important. And a company, ISRO, has put together this tool that is called the Sentinel-1 Explorer. And Dr. Podest alluded to that there's other radar instruments up there. And one of them is this one put up by the European Union called Sentinel-1. There's things that you can read all about it, including on this website. And so here, if I can find my chat, there it is. I will drop this into here so that you can actually jump back, and explore your particular area. And so again, to allow us to put these things together, right? Let's zoom back into this area that we were just looking at. You can see here's those two big lakes that we were looking at initially. And we were down in this area looking at these particular sort of gray things that are just taking a little bit of time. But you can start to see the wetland areas turn out in this visualization as sort of this purpley color. Okay. And so you can actually see, as we zoom in, we can start to see how people have manipulated this, right? And it's just really fascinating to start to see the colors. And again, here, the forested wetland areas are this purpley color. And areas that are just forested, that don't have that really wet soil, maybe it's standing, maybe it's just wet, they are in this yellow color. Okay. And you can spend some time going through and learning how to understand this radar signal in the many ways that Dr. Podest highlighted for us today. And the key is you're just looking for differences on a map like this. What are the differences that are showing up? Where are some patterns that are all yellow or all red? And that's what allows us to put together and understand, again, where is the water permanently on the surface, like these water bodies, versus areas where it's doing some of that complex bouncing that Dr. Podest highlighted. So this is a great tool to just start understanding the radar signal in your particular area. You can use this tool to actually get at some of the data, some of the information. You can read all about that here, what it is that's actually getting measured. How does this relate to this new sensor that is, again, on the horizon for all of us to start using? And importantly, it will start filling in this missing information about what is happening underneath the tree canopy that we tend to focus on so very much when we look at our imagery and our data. Okay. So I wanted to end with this one because it's a fun way that you can actually start seeing some of this radar data. And the more you spend your time looking at your study area and other areas that you know, the better off that you are. I want to stress that this information is hard to find. Okay. So when we talk about wetlands, we've highlighted EarthMap before and various other data sets. I've had a hard time finding anything that really shows us where forested wetlands are located around the world. So please join us in, doing this documentation and helping us even with just some ground photos and some description about, how wet or dry is that soil. That's the kind of information that we need to be able to help somebody like Dr. Podest and all the other people that she's working with around the globe. So I hope that dive into radar data is both a little intimidating, but also you could see the way that we are here to support you. We're here to facilitate looking at the data, which leads to going out and investigating just why are we getting the patterns and the numbers that we are. So with that, I didn't see a lot of questions over here, in the chat, but as you can see, we've really got a wonderful suite of ways of understanding the world around us. And, and what I want to highlight here is remote sensing has two different activities. And the first one that we want to really stress is simply using the sunlight to show us what's around us. This is what our eyes do. This is what Globe Observer does. And that requires knowing how much sunlight is coming to us. And so if you want to take the next step and actually measure that sunlight or that reflectance in a wetland area or an area that has wet soil versus dry soil, go a little bit deeper beyond just taking these mobile photos that we're doing with Globe Observer, our down photo. Bring in, as John Moore highlighted, bring in Stella as a way of making those measurements. Again, you are measuring how much sunlight is filtering through that tree canopy cover or shrub canopy cover to actually get to the soil surface. And the more illuminated that surface is, the more and quicker it tends to dry out. Okay, so that's one thing to recognize. And if it's not drying out, that might indicate, again, different numbers and measurements that you'll get with making those Stella measurements of sunlight, as well as what we're going to record and what we were going through and seeing in the way that the sunlight reflects off that surface. So it's really fascinating. And if you take that next step with Stella, you can actually, we've highlighted Stella before as an instrument that you can use in your classroom to model a wetland environment. So you can actually find like an experiment with the amount of water in, combined together with soil or dirt or some other things like that. Make those measurements with different amounts of soil moisture, and you will actually see a different spectral or sunlight reflectance response based on that. And the color of the soil makes a big difference here. So there's a lot of things that you can model that we talked about here today. And then if you go out and actually make these measurements using sunlight, that's where we start getting some variability in the world, because that's, not everywhere is the same. So that's a difference between being in control in the lab and testing out some of these ideas and how sunlight will reflect off of it. But then you can also do the active piece. And this is what Brian has been talking to us with lasers and ISAT-2, right? And with the radar piece. We know how much energy is going out. And so that actually makes it easier for us to measure something with Stella or with some of these other instruments, is we know what should be coming back to the instrument if nothing gets in the way, right? And that was that first piece of what type of surface are we actually measuring. And so that surface roughness is the fun that we are experiencing and get to go through. And I want to highlight for John Moore, Stella does have a LiDAR, at least for one of the versions of Stella. You have a LiDAR that allows you to look at that green light reflectance, or the 918 nanometer wavelengths that you're measuring there. And again, how does this moisture in this environment change the signal or the measurement that we're getting? So that's your challenge for this week or this month, is to go out and start to see what is happening, as water comes into your environment or as it starts leaving. And when we're going to be having some intensive optical observation periods to really reinforce this idea of optical measurements, like what we're doing from space, like what we're doing with Globe Observer, that is slightly different than a direct measurement. And so, we've used this term intensive observation period, and I want to really help you to understand how these optical images turn into knowledge. And this reflection and what Dr. Podest highlighted for us today are ways that we can actually help these upcoming missions. And I hope that you're as inspired as I have been, to bring this excitement and this very relevant science challenge to our community and our trees around the globe, mapping and measuring challenge that we've been doing for the 7 years, right, Brian?
Exactly. Yeah. Thank you. That's such a, you tied everything together so well with showing those. Yeah. And I really need to look at the that Sentinel Explorer a little better, a little more, because I haven't paid attention to it for a while, because, you know, I put in the chat there that, you know, SMAP mission, Soil Moisture Active Passive, launched back in 2014. And, you know, about 3 months after launch, it lost its radar. Its radar just stopped working. So NASA had to really scramble to figure out, wow, we need this radar because we need to get this higher resolution data. We have a radiometer on board, so we're just looking at it passively, which doesn't give us the good resolution. A combined one is what you need. So then they started looking at Sentinel-1 with the European Space Agency, and realized that satellite flies close to SMAP and has an active radar. So they combine that too, and we actually have really great combined data between Sentinel's radar and SMAP's radiometer. So, you know, that's just one small part of it. But yeah, thank you for tying it all together at the end. I think that you know, it's great. And thank you, John Moore, for the Stella question as well. And before we go, let me, I'm going to share something really quickly in case not everybody knows. Let me, window. All right. So last week on the Globe Observer, if you haven't updated for a while, you will not know this, but there has been added to the trees tool on the Globe Observer an optional observation to include the genus and species of tree that you're measuring the height of. And you can, there's a whole list of ones when you go into the Latin name. When you start typing it, you can look, it'll show all this whole list of ones to choose from. Okay, this one happens to be a loblolly pine, the Pinus tata, and that's the loblolly pine. And this is one that I did over near our Wallace Visitor Center. And you can it actually asks you too, what is the source of your information? Is it identified via an app? Is it a guide, a classification guide for trees, or is it something else? And then you can put his common name here. And this is huge for a lot of reasons. One is, as you know, different types of species of trees pull in different amounts of carbon dioxide from the atmosphere. So it's not a uniform, you know, pulling in of that carbon dioxide, not a uniform carbon sequestration for every tree species around the world. But then also our friends with the trees around Latin America and Caribbean region for Globe, they're really working on a project on mangroves right now. They've started this, and they're doing mangroves, but they also want to be able to identify different trees when they're taking observations. So this is one of the reasons why we did it. We did it for everyone because that's a lot of people want to know what the heck trees they're looking at. And we understand that not everybody knows, or they don't have an app installed on their phone, but you can get something like iNaturalist. You get something like the CCAP by an iNaturalist. I use the CCAP all the time if I want to try to identify a critter, you know, a bug or a plant or flower that I don't know what it is. And it's really good. It goes into a database of, you know, probably a million different things to choose from. So it's really good. But I wanted to, if you haven't updated your Globe Observer lately, when you go into the app on your phone or tablet, and make sure you accept the update, because it will include this as part of it. And I believe there is now, or will be extremely soon, as part of the tutorial, a couple pages talking about the genus and species optional observation on the Globe Observer Trees tool. So I just wanted to highlight that for you, and make sure you check that out. But thank you everyone for being here, and you know, stay tuned for an email with mentioning that this recording that is online. And the recording, as you know, when it's online on the webinar page for the campaign, we have all the links that we put in with the chat underneath there. But then also stay tuned later today for an email about our collaborative webinar for December of 2024. So thank you, everyone, and we'll see you next month.